Thank you and good afternoon, everyone. Thank you for coming to my talk, AI on Tracks, How Trams Are Learning to Think. When people hear AI in tram, they sometimes imagine two extremes. Either a ChatGPT-powered tram that starts writing a poetry, or a runway Tesla with rails. The truth is a lot less dramatic and a lot more interesting. My name is Marina Ionova. I am a robotic engineer at Škoda Digital. I spent past years developing and testing anti-collision system on real trams, including here in Prague on the new 52T model. Alongside my engineering work, I've done research and published, so what I will share with you today is not marketing, is not science fiction, but real experience from both practice and research. In this talk, I will show you how AI is already being used in rail today, why we cannot just copy-paste automotive technology into rail, and what it takes for AI to actually meet safety standards that trams need in real cities. So let's begin with the obvious question. Where is AI already being used in rail today? And of course, first is safety. The most obvious and the most important area. And when we start talk about safety, the first application that usually comes to our mind is collision avoidance. Its job is simple: to prevent crashes in unexpected situations by triggering emergency braking when the driver does not react, maybe distracted or suddenly unwell. And let's take a look how it's work. So there are many sensors like camera, LiDAR, radar, odometry, etc. And then it starts with object detection. Most often it's handled by convolutional neural networks like YOLO or faster RCNN, which can recognize pedestrians, cars, cyclists, and other trams. Also in parallel, classical methods like image segmentation or point cloud clustering is also used for add redundancy to the safety critical settings. The next is a trajectory prediction, estimating how fast and in what direction an object is moving, whether it is likely to cross the tram's path. Some systems keep it simple with kinematic equations, while others experiment with a recurrent neural network for short-term motion forecasts. And the final stage is a risk assessment, deciding whether a collision is imminent and when braking must begin. This can be done with classical physics-based braking models or with learning-based classifiers that estimate collision probability from multiple signals. And still, in this area, there remain many challenges. The first is certification. So, aligning neural networks with safety requirements is still a nightmare. And we will talk about it in more detail a little bit later. The second limitation is limitation of sensors and algorithms. So, for example, at 70 kilometers per hour, a tram's braking distance approximately 90 meters. Also, we need to add 1 or 2 seconds to the driver reactions. That means that a hazard must be detected over 100 meters away. That's okay, maybe not such a big problem during good weather, but during hard fog, rain, snow, even with a small object like children's or with a black cars which has a low reflectivity surface, it's really challenging. And the last but not least is a human trust. too many false positives and the driver stopped believing to the system with deadly consequences in a real emergency. But safety is not only about what happens on the tracks, it's also what happens on stations. So I prepared three use cases for AI, which already been implemented. The first is unattended bag detection. So cameras watch station and neural networks like, one more time, YOLO or CNN look for people and bags. Then the system links each bag to its owner and tracks them together with a sort or Kalman filter. If the bag left alone, it raise an alert. The next application is a fall detection. And there are two main approaches. The one tracks a person body posture and flags if someone goes from standing to lying down by changing the vertical to the horizontal position, changing body angle, or, for example, center of gravity. And the other looks at the short video clips and recognizes the action of falling. So uses models like 3D CNNs, two-stream networks, or transformer-based video encoders. The model directly classifies the action as falling, walking, sitting, etc. by learning motion patterns. The next application is coupling monitoring. The camera monitors the coupling zone, and if the dangerous event is seen, such as a person climbing between two couples, it raises a visual and acoustic trigger to the driver. And let's take a look on the challenges. Of course, false positives, so palms mistaken for bags, people sitting mistaken for falls, and that means only one, that human in the loop is still needed here. The second challenge, many of those applications are based on the computer vision technologies, which can work not so perfect, for example, during poor lighting or on crowded platforms. And the last challenge, but not least, that GDPR treats all passengers' video and the personal data. Consent is not practical in the stations, so operators must rely on public legitimate interest, so with really strict limits. And also, EU AI Act will soon classify those as a high-risk data. That means that it requires logging, audits, and human oversights. And if the safety and, for example, anti-collision system is a sexy part of AI, predictive maintenance is a quite powerhouse. Because there is many data from, for example, from onboard telemetry, like vibration, current, temperature, doors, brakes, motor, etc. Also, we can get data from infrastructure monitoring, like track geometry, ultrasonic tests, drones, robots with lidars and camera. And I'm not kidding, for example, here, you can see the robot from the Dubai Metro, which scans tunnels at night, reducing manual inspection hours. And all of those data then can be used for example, anomaly detection, prognostic estimating, useful life, vision models, spotting cracks, vegetation, and optimization tool that turns prediction into maintenance schedules. And machine learning models as good as their training data. Unfortunately, in rail, failure logs are often incomplete or inconsistent. And even a well-trained model can drift. For example, new parts, retrofits, or extreme weather can change the signal patterns, so the model's no longer matches reality. And what about passengers? Passengers don't see algorithms, they feel delays, queues, confusion. And AI is now quite helping here too. For example, in India, Ask Disha 2.0 answers billions of questions daily about booking and refunds in multiple languages. Also in Hamburg, Munich, and Berlin show carriage level occupancy on the platforms, so letting passengers spread out. Also in the Middle East, similar systems were deployed across 100 train sets for the major events. And in some trains in Germany, computer vision system monitors the platform and train doors, so to see if there is a person with a wheelchair waiting to board. The system alerts the driver and automatically extend the closing time to give the person enough time to get off and on safely. And what about challenges here? First, of course, hallucination. So generative chatbots must be grounded in official data. One wrong answer and the person will end up on the other side of the country than he needed to be. Also, the grounding models need to adapt really fast during special events or incidents. And of course, all of this touches personal data, so GDPR and AI Act impose strict transparency, minimization, and oversight. And also behind the screen, AI also makes rail operation more efficient. In Germany, S-Bahn control rooms use AI-assisted dispatcher tools to simulate conflict resolution and recover up to 8 minutes of delay. So for Deutsche Bahn, I think it's a really big step. In German and French, operators run eco-driving advisory system. So in metro, AI schedules acceleration so that regenerate braking from one train to power another. And in the UK, runs a digital twins with machine learning demand forecasting to test timetables. And of course, in China, central AI integrates dispatching, energy, and simulation for 40,000 kilometers of high-speed rails. And let's take a look on the challenges. So, predictive maintenance, predictive models are never perfect, and we still need to find the way how to work with uncertainty. Then, either with an AI, NP hard scheduling problem does not get either. And then a human trust, so operators and controllers must understand why AI suggested an option. And the last, certification, so optimization is fine, but it's not yet certifiable. So far, we have looked where is AI already being used in a rail today, so passengers app, assisted safety assistance, predictive maintenance, scheduling and optimization, and of course I didn't cover the whole spectrum of applications, but I know what you're probably thinking about, that those applications are nice, but when do we get the real deal, like a driverless trams? Because if cars in Arizona can already drive themselves throughout the traffic, then surely a tram, which literally follows the rails, should be even easier, right? Just point them forward and do the AI and let the AI do the rest. Well, not exactly, and let's take a look on the main differences. The first is a movement. So car can go around and turn. Trams can only brake. And that changes everything for safety systems. And the second point, how to brake. A car stops in meters. A tram in dozens of meters, so physics does not negotiate. Then, car carries one family. One tram carries a city block with hundreds of passengers on board. So risk scales with people. And from the point of view of the cybersecurity, one car protects a single vehicle. Real must protect entire network, including decade-old infrastructure. And of course, a car lasts a decade. A tram is expected to run for 30 and more years, so technology must keep up. In short, trams and cars face different environment, physics, safety standards, and risks. And we can bring some ideas from the automotive AI, but direct transfer will never works. And that's why AI needs solution built for its own unique challenges. And because the risks in rail are higher, with 100 passengers on board, with no option to steer away, the rules for safety are also much stricter. And that's where the real challenge begins, taking the AI idea from lab and proving it reliable enough to earn certification. So let's talk about how that journey looks like, from research to deployment and the safety standards like safety integrity level, which define where a tram can truly operate without a driver. To explain this, we need a special scale, which is a grade of automation. At the first level, trams drive, the driver still control movement, doors, etc., but systems assist. For example, by reminding speed limits, detecting potential collision, or taking doors for passengers or obstacles. At the second level, the trams drives itself, but drivers stay in the cabin as a backup. At the next level, the tram drives itself, but there is no driver's cabin. But one person from the staff should be present on board for any emergency situations. And at the first level, trams drive themselves without no human on board. That is the 4 steps of automation, and at each step, requirements for safety and reliability increase really dramatically. That's where another acronym appears, safety integrity level. Let's answer one question. How reliable is a system at preventing and reducing risk? The higher the safety integrity level, the lower the acceptable probability of dangerous failure. And failure here means when the system should act, but does not. Let me put safety integrity level into everyday language. So, at the first level, your car alarm that does not go off during a break-in. I know it's annoying, but not life-threatening. Another level, a machine tool automatically shutting down when it overheats. Mistake here could already hurt people. The third level, a system that automatically brakes tram or train if a driver ignores a signal. Failure here risks collision with dozens or hundreds passengers at stake. And the first level is a nuclear reactor control. A single mistake here is a catastrophic. So at this point, you're probably asking, how are those probability actually calculated, and what do they mean for me, for us as developers? Let's break it down using collision avoidance system as a reference point. So the first step that needs to be done is to define operational design domain. The exact condition when and where the system is allowed to work. So, for example, weather, lightning, trucks type, location, etc. And the system also must know when it's outside of the operational design domain and shut down safely. The second step, we need to perform safety analysis, such as hazard analysis and risk assessment. And during this step, we need to identify what could go wrong and how dangerous it would be. And from this, we can calculate a tolerable hazard rate. For example, for safety integrity level 2, not more than 1 times 10 to the power of -7 hazardous collision per hour for collision avoidance function. And the third step is implementation. And railway software is built under strict standards. Those does not regulate a code, but the whole process. Requirements, documentation, integration, testing, validation, verification, etc. So the idea is that the safe software comes from the safe process, not just safe code. And here comes the fun part, because the traditional software is relatively easy to integrate into this process. We don't need to calculate a failure rate for a software code, because we prove its reliability throughout a process discipline. But with machine learning, things get interesting, because safety integrity level demands predictability, traceability, and explainability. Neural networks and machine learning are statistical, adaptive, and hard to interpret. Two worlds that naturally does not match. And also in neural networks and machine learning, the result depends on the training data. So it can be unpredictable in unknown scenarios. And that's why it's really hard to formally verify the entire model. But let's still try to figure out whether a neural network can be aligned with safety requirements, for example, of safety integrity level 2, and what it would need to achieve. In the previous step, we discussed that tolerable hazard rate for the safety integrity level 2 must be 10 to the power of -7 per hour. Let's run a simple calculation. Don't worry, not anything complex. Imagine that we have a collision avoidance system with 1 camera and 1 LiDAR, using 1 out of 2 voiding principle, without any complex logic on top of it. So the question is, what recall does each neural network need to achieve for overall system to meet safety integrity level 2? Also, we need to define a probability of hazardous situations. So let's say it's 10 to the power of -3 per hour. And also we need to define a probability of simultaneous means by both sensors. Let's say it's 20%. And the probability of the dangerous fail then can be calculated with a formula where the first part present a common error. So, for example, during a hard rain, camera cannot see anything, and LiDAR also cannot see a black car because it has a low reflectivity surface. So both sensors miss this car. And the second part define coincidental misses, so both sensors fail independently. To convert those probability of dangerous failure to per hour, we also need to multiply it by lambda, which we defined before. And putting the value in, we find that each sensor would need to achieve a recall about 99.95% on hazardous events. Not on every frame, but especially on object within a braking distance. In real city conditions with pedestrians, cars, trams, cyclists, rain, snow, and endless distractions, reaching 99.95% recall on hazardous events sounds almost impossible. But do we have tools to make it realistic? For example, we can limit detection to the actual braking corridor, or propose the architecture where AI will always cross-check with another algorithms. Also, we can define a stricter operational design domain, so where the system is allowed to work, but to be honest, who would like to buy a system that's work only sometimes? And of course, we can use a sensor fusion, so cameras, LiDARs, radars working together. In Metro, at grid of automation 3 and 4, at safety integrity level, three safety systems are already in use. For example, metros in Dubai. In automotive, 98% of recall on pedestrians is considerable enough under automotive standards, but for trams, we need better. A single neural network will not achieve it, but the right combination of technologies, it become possible. And that's we only talking about false negatives, but the false positives can be also dangerous. Just quick check, who here has been on the trams that it slammed into emergency braking? Do you remember it? Yeah, I have, likely I was seated because most of standing passengers fell to the floor, and I almost broke a tooth at the seat in front of me. So that's why it's why false positives is matters too. And now I think it's a right time to finally answer the main question of this speech. So, how are actually trams learning to think? Thinking starts with perception. For a tram, that's not just cameras spotting pedestrians. That's about LiDARs, radars, even diagnostic sensors which monitor brakes, wheels, and motors. A modern tram can see the street and itself, so both the world outside and the health of its own. The next come prediction. AI models forecasts if an object will cross the tram's path, if a wheel set is about or veered out, and or if I don't know, today crowding will overload one carriage. So this is where AI and machine learning shine. So finding weak signals before they become a real fail. Or for example, giving passengers more accurate arriving time instead of voyage delayed messages. And then comes the hard part. Decisions. Should the tram brake now or wait? What train gets priority in a junction? How do we adjust the timetable after a disruption? So here, trams combine classical physics models, optimization algorithms, and yes, still human in the loop. So it's not AI replacing drivers or dispatchers. It's AI giving them better and faster and informed choices. And finally, integration. A tram is not clever because of one smart algorithms. It's clever because perception, prediction, decision-making are tied together into systems that meet strict safety standards, like safety integrity level or cybersecurity frameworks. AI becomes trustworthy only when it's embedded in processes that regulators, operators, and passengers can rely on. So, how are trams learning to think? They are not dreaming of freedom, they are learning in a very practical way to perceive their environment and their own health, to predict risks, fails, and passenger flows, to decide with optimization and human oversight, and to integrate safely into complex city around them. That's not science fiction, that's a real working AI already shaping the way how we move throughout cities. And as much as I believe in AI, please let me finish with this. Never challenge a tram to a braking context. Physics always win. Thank you for your attention.
I love the final remark, physics always win. So if you have any questions for Marina, please use the Slido. So I see you scanning. I'd have one question. How come you end up in this field of, research and work? Wow, I mean, this is pretty impressive for me, and it's pretty specific, actually. So what's the story behind?
So I met HR people at our student club event. So we organized this as soft skills courses, and there he presented the Skoda transportation and this project. But during this presentation, I was at the bachelor, so I think, oh, okay, it sounds interesting, but I thought that it's located in a Pilsen, so it's not fit to my location. But when I start looking for work after my master degree, and I find it's on the LinkedIn, so I say yes. So autonomous trams sounds amazing. Let's do it.
Okay. Yeah, I have a question. It took me a little bit longer. I had to restart the Slido. But we have a question from the audience. Why AI application in Rails do you find the most promising personally?
Oh, of course, anti-collision system, yeah. Because, without a joke, because it can save someone's life.
Okay, one more question coming up. Decision making. Don't trams slow down normally immediately during that phase and only then emergency? I'm not sure if I follow the question. Do you understand the question, Marina?
Yeah, if we using only emergency braking or normal like a...
Hold on. I don't see you. Who is talking? You. Sorry, I'm gonna give you the mic.
No, my question was if the tram shouldn't slow down immediately when something is suspicious and apply the emergency braking when it is decided. If it works this way or not.
So, as I mentioned, using an emergency brake is not good for passengers in the trams, and it's two different applications. Anti-collision system only needs to prevent unexpected situations. Also, there is a ATO, which is, if am I right, autonomous train operation, so which can drive this tram and also recognize the obstacles in front of the tram, so it can slow down more smoothly with using service brake, and like combination of this application we can reach the autonomous tram. So it's two different works, but then it's combined together like for a smooth operation.
Okay, thank you for that question and for the answer. And I see there only one more question, so it's probably the last one. It's, hey, do you know about any integration camera surveillance network to cooperate with public transport or rails?
I'm not sure about cameras because mostly I work with LiDARs. So let me contact on LinkedIn and I can ask my colleagues if they know more information about camera.
Thank you very much. And just let me double check. No, there is no more questions. Anyone, would you ask anything here in the audience? No? Well, thank you, Marina, for your talk. Please don't forget to give us feedback and give Marina the feedback and rate this session. And as I already mentioned, this was the last one here on the Universe Hall, on the Universe stage. But there are also lightning talks in the forest door in the main one, and also closing ceremony right after the lightning talk. So if you feel the urge to share something with the audience, please do during the lightning talks, and also please join us for the after party which follow straight after the closing ceremony. Give it up to Marina. Thank you very much, Marina, as a last speaker.
Thank you for having me.
Thank you, guys.